Hi folks, welcome to the Math 621B Chapter 9 Concept Roundup. In this chapter we're looking at rational functions. As always, this is not an exhaustive look at all the topics, but it's a pretty good sort of roundup of the important ones. These are the three topics we'll be looking at. There is a downloadable copy of the notes in the video description below, as well as a downloadable review sheet. So let's dive in. If we think about our basic hyperbola that we looked at in, say, Chapter 1, we'd have 1 over x, and that graph looks like this. It's got a bunch of features. It contains the point 1, 1, and negative 1, negative 1. But most importantly, it has asymptotes. It has the y-axis as a vertical asymptote. Okay, and the y-axis has an equation of x equals 0. And it also has the x-axis as a horizontal asymptote. Which is the equation y equals 0. If we want to mess with these and transform them, then the basic sort of form we deal with would be something like this. Y equals a over x minus h plus k. And the parameters do their usual stuff. This moves us, or shifts, left, right, or horizontally. This is our vertical shift, or vertical translation. And the a functions as our vertical stretch factor and if it's negative, it causes an x-axis reflection. Okay, so with that in mind, let's do a sketch of one of these transformed functions. Right over here, I've got one of these hyperbolas, which I often think of as a butterfly. The shape is a butterfly. And let's see what's going on. We've moved left 1, and we've moved down 2. We can also say that there's a vertical stretch by a factor of 2, or by a factor of 3, rather. And there's an x-axis reflection. If I want to go and make this graph, the most important things are the asymptotes. So we've moved left 1. That's going to move our vertical asymptote to the left 1. Instead of being at x equals 0, it now has an equation of x equals negative 1. If I want to go and do my horizontal asymptote, well, that's been moved down 2 units. So now it's going to be at y equals negative 2. And I always show my asymptotes as dotted lines. We want to find a couple of points to be able to put on this. So I might make a mapping rule. You don't have to, but here I know that any point x, y is going to be mapped to. Well, let's see. The x's go to the left 1. The y's, they get stretched vertically by a factor of 3. They get flipped upside down with the x-axis reflection, and they go down 2. I can think about the points that are on a basic hyperbola, or basic butterfly, and then I just map them. If I put in 1 for x, well, I'll get 0 on this first one. If I put in 1 for y, I'll get negative 5. There we go. There's a point that's on this graph, 0, negative 5. I better continue this down further. If I put negative 1 in, for x, I'll have negative 2. And if I put negative 1 in for y, I'll have positive 1. So it contains this point. And now all I need to do is draw around those new asymptotes. So the same shape as we had up here, but now around these asymptotes. And you can see instead of starting in the top right, it's going to start in the bottom right. And that's because we had an x-axis reflection. Same thing over here. Make sure you actually cross the x-axis now, because the new asymptote is this line, y equals negative 2. And there's the basic look of the graph. That's a transformed butterfly. Sometimes we get these functions that are fairly easy to deal with, presented in a different way. We might have them as the ratio of two linear functions like this, 2x minus 3 over x minus 1. But we really prefer them in this format. If you put it into a graphing calculator, well, it doesn't care about the format. But for us to analyze, we want it in that format, where it's got a whole number and then it's got a fraction. And we can get to that form using long division. Now, if you don't feel that this is a yay moment, that's okay. Maybe it's yay, maybe it's not. But it does get us to go from here, y equals 2x minus 3 over x minus 1, into some form we can understand. Okay, so if I want to do this, make this graph or describe this graph, here's what I do. I'll perform this division. So I'll go 2x minus 3, and I'll divide it by x minus 1. And yes, you could use synthetic if you prefer. Okay, and we go 2x divided by x, that's a 2. Now I multiply that on down, and I'll get 2x minus 2. And I'll remember that I'm subtracting the whole thing. So that'll give me negative 1 as my remainder. Okay. And if we think back, that means we can now rewrite this function as y equals 2 plus the remainder over whatever we were dividing by. Now that doesn't look exactly like what we want. But if I just switch the order, if I put the remainder part first, now we know what we're dealing with. We're dealing with a butterfly that has moved right 1, up 2, and has an x-axis reflection. And if we went through the process of actually going to make a graph, it would look roughly like this. And since it had an x-axis reflection, it would exist in these quadrants. Let's go through that process on one that's a little more involved. Just to refresh our memories, if we want a y-intercept on any function, we sub 0 for x. If we want an x-intercept, we sub 0 for y. So here we're going to find out as much as we can about this function. So the easiest thing to find out about it would be the y-intercept. Okay, if I put in 0 for x, I'll have 0 here, 0 here. So I'd have negative 5 over negative 2, or 5 over 2, or 2.5. Now, if I want to go and find the x-intercept, no big deal. I just put in 0 for y. So I'd have 0 equals 4x minus 5 over x minus 2. And you might think, well, that kind of looks like a miserable equation. But the only way for that fraction to be 0 is if the top is 0. So you could think of it as multiplying both sides by x minus 2, or just getting rid of the bottom. Okay, so if you like, we can do this to show what's going on. But you still have 0 on the left-hand side. Now we'll have 5 equals 4x, or x is 5/4, or 1.25. There's our x-intercept. So if I want to start to graph this, I know about a couple of points on the graph. I know that it contains a y-intercept of 2.5. 1, 2, 3. There's 2.5. And an x-intercept at 1.25. So right here. Okay, beyond that, we're really not quite sure what's going on with the graph. So we're going to convert its form, just like we did in the last example. We want to get it into that a over x minus h plus k format, so we can see what transformations are happening. And again, the way we'd get there is through long division. I divide this out, I'll get 4. Multiply it back in, 4x minus 8. Subtract it all off. That gives me 3, or a remainder of 3. So that means the function can be written as 3 over x minus 2 plus 4. Aha! Now we know what's going on with this function. It's a butterfly that's moved right 2, up 4, and vertical stretch by a factor of 3. Okay, let's put in those asymptotes then. If it moved to the right 2, it now has an asymptote at x equals 2. If it moved up 4, that means it now has a horizontal asymptote at y equals 4. And those are really important for these types of graphs. That's what we hang the whole thing on. Okay. From here, we could go and map the other points, or we could just start to connect the points we know. Clearly, in order for us to connect those points, we have to exist down here to the lower left. And the other part of the graph is going to be up here. If you wanted to, you could also map your basic points. Okay? And that would be using a mapping rule, something like this. This is moved right 2, vertical stretch by a factor of 3, and up 4. And you would just take the points 1, 1, and -1, -1, key points from your basic butterfly, and plug them in to give you 3, 7, and 1, 1. Okay? And that really does look like it's on the graph. There's the 1, 1 point. And up here, we'd have the point 3, 7. We still get the shape even without it, just by analyzing it. So that's about all we can do with a basic hyperbola, with a basic butterfly graph. Find the axis intercepts, convert it into this nice form, describe, and then make sure that we've got our asymptotes on. The last thing you might be asked to do is to get the equation from a graph. So here I've got one shown, and I even drew in the asymptotes. There's an asymptote at x equals -3, and there's an asymptote at y equals 1. So let's imagine what's going on with this graph. If we were to put its equation in, I really don't know what the vertical stretch factor is. But I know that it's been moved to the left 3 compared to a basic one. So that must mean an x plus 3. It's been moved up 1, so it must mean that we've got a plus 1 tacked onto the end. In other words, h was -3 and k was 1. Okay, this is still not good. We've got 3 letters. We would like to just have an x and a y in there. So we'd like to find out that a value. And the way we can do that is to substitute in the known point. That'll get us down to just one letter. And when you have just one letter, you can solve. So we're going to substitute -5, 2, which is a point on the known curve. 2 goes in for y. A is unknown. -5 plus 3, all plus 1. Okay, I'm going to move that 1 over to the other side. So I have 1 equals a over -5 plus 3 is -2. Multiply both sides by -2, and I'll get a equals -2. Meaning that the equation of this graph should be a was -2 over x plus 3 plus 1. Okay, here comes the exciting moment, the big reveal. Is it actually that equation? Oh my gosh, we nailed it. So we got the reflection in there, we got the stretch, and we got the translations. The next big topic is analyzing rational functions. And these are ones that might have quadratics on the top or bottom. And here's what we need to know. Any factor that only appears on the top corresponds to an x-intercept. Any factor that only appears on the bottom is a vertical asymptote. And factors that appear on the top and bottom can be divided out, but they're going to represent holes on the original graph, meaning the graph is undefined at those points. Okay, so let's find all these x-intercept asymptotes, only vertical asymptotes for now, and points of discontinuity. So on this one here, x-intercepts, that's factors of only the top. That would be this x. What makes that 0? Well, 0. So 0 is a factor of the top only. Now the bottom only, I don't really know. If I want to see its factors, I really have to factor it. And I should have started with this, really, to check for factors that appear maybe on both. So if I factor the bottom, I get x minus 3 and x minus 1. Those are going to be our vertical asymptotes. There's a vertical asymptote at each of those factors to the bottom, namely where x equals 3 and x equals 1. And here I do have to write x equals because I'm talking about a vertical line at 1 and a vertical line at 3. If you went and grabbed a graphing calculator and graphed that function, you would find a vertical asymptote at 1 and 3. Okay, finally, points of discontinuity, or holes in the graph. Those would be factors that appear on both top and bottom. Well, let's see. We've got an x on top. We've got an x minus 3 and an x minus 1 on bottom. There's nothing that appears on both top and bottom. So there are going to be no holes in this graph. Taking a look at the next one, for us to analyze it, we really need to factor it. So the top is x plus 2 by x minus 2. The bottom would be x plus 4 by x plus 2. Okay, so let's hunt for some x-intercepts. They are factors of only the top. So take a look at this one here. You might say, oh, well, that's going to be an x-intercept. But it's not, because it appears on both the top and bottom. You've got an x plus 2 on top and bottom. That's going to be a hole, or a point of discontinuity. So that will occur at the x value of negative 2, whatever makes those brackets 0. We'll deal with the corresponding y value in a minute here. Going back to the x-intercepts, they're factors that only appear on the top. So that's this one right here. There's going to be an x-intercept at 2. X minus 2 means a factor of 2. Vertical asymptote. Those are factors of the bottom only. That's right here. That's that x plus 4. Okay? Which means that there's a vertical asymptote at x equals negative 4. Okay. Lastly, we want to figure out where this point of discontinuity is. Now, I think it's really enough for us to say that it exists, that the point of discontinuity is where x is negative 2. To say that it doesn't exist for a specific y value 2 is a bit of a stretch, but there are good reasons for us to consider that as well. So here's what you do to figure out exactly where that hole is. It's definitely where x is negative 2, because that was a factor of the top and bottom. I can then go and cross those out and say this function is really just x minus 2 over x plus 4, as long as we don't use a value of negative 2. Okay, that's the illegal number to put in there. But if I want to find that point of discontinuity, I put it in anyway. So I would have negative 2 minus 2 all over negative 2 plus 4. Okay, which would be negative 4 over 2, or negative 2. So on this graph, whatever it looks like, At -2, -2, there's going to be a hole. It'll be continuous around that, but discontinuous right at that hole. Okay, so that deals with vertical asymptotes, x-intercepts, and points of discontinuity. There's one last piece of the puzzle if we want to be able to analyze and generate graphs for more complicated rational functions. And those are the horizontal asymptotes. So we say for functions of the form f of x over g of x, if the highest power on the bottom is bigger than the highest power on top, so if the bigger degree is on the bottom, then the horizontal asymptote is going to be y equals 0. So I'll give you an example of that. You might see something like this written. h of x is x minus 2 all over 2x squared plus x. Bigger powers on the bottom. As soon as that happens, it's really the bottom that's driving the function as you go towards infinity. So the bottom's getting really, really big. And if the bottom of a fraction gets big, that means we tend towards 0. So what this means is a horizontal asymptote of y equals 0. Anytime you see the higher power on the bottom. If the degrees of the top and bottom are the same, so the highest power that you see on the top and bottom are the same, then we'll have to find this horizontal asymptote, and it's pretty straightforward. So if we had something like this, one quadratic over another, you can see the degree of the top is 2, the degree of the bottom is 2 as well. Here's where the asymptote will be. You take the highest power of the top, 2x squared, and divide it by the highest power on the bottom, which is just an x squared. Okay, and what does that give us? 2x squared over x squared gives us y equals 2. So we just divide out the highest powers on top and bottom, as long as they're the same on both. Sometimes people just think that means it's going to be the coefficient of the first one. That's not true. Here's an example of that. You might have 3x minus 1 all over 5x plus 3. So your horizontal asymptote, and this is just about the horizontal ones, is going to be highest power of the top divided by highest power of the bottom, or y equals 3/5. Last case, if the highest power is on top, there is no horizontal asymptote. So you might have something like this. M of x is 2x squared plus 1 all over 5x minus 3. You can see right away, highest power is on top, no horizontal asymptote. And we need to keep all these ways of analyzing the function straight so that we can go and analytically come up with the graphs of different rational functions. There may be, in these cases, maybe a horizontal asymptote, or rather a slanted asymptote. That's not really in the curriculum, but I'll put it in an example at the end of the video that you might want to watch, or you might not. Okay, so here are a few examples. We want to find the horizontal asymptote, if any. Take a look at this first one. Same power on top, same power on bottom. We just divide those terms out. X squared over x squared, which would give us y equals 1. That's the horizontal asymptote. Take a look at the next one. Degrees are the same on top and bottom. So again, we just divide them out. 2x squared over x squared, y equals 2 is our horizontal asymptote. In C, higher powers on the bottom. What does that do? Horizontal asymptote is y equals 0. Whenever the higher power's on the bottom, we get this. And the last one, higher power is on the top. no horizontal asymptote. And again, at the very end of the video, I'll go into one of those, but it's not in the curriculum. Okay, so now that we were able to talk about the horizontal asymptotes, we're going to go and take 3 of those 4 last functions, and we're going to generate their graphs. And we're going to use these 5 key ideas. That we can find the y-intercept, horizontal asymptotes, x-intercepts, vertical asymptotes, and points of discontinuity. And I think it makes sense to do them in this order. So the y-intercept just means subbing 0 in for x, 0, 0, 0, 0. You'd have -2 over -4, or a half. Horizontal asymptote, same power on top and bottom. We actually just did this. So that would give us y equals 1. And since it is a line, we do need to put its equation. We need to put the y equals. So already I know a couple of things about this graph. I know it has this asymptote at y equals 1. And I know it has this y-intercept. Okay. The next few things I'll need to factor before I can figure them out. So let's see, that's x plus 2 by x minus 1. And then on the bottom, you'd have an x plus 4 and an x minus 1. Great. X-intercepts are factors of the top only. That would be this one right here, or -2. Okay. So while we're at it, why don't we go and put that point on the graph. Vertical asymptotes are factors of the bottom only. So that's going to be x equals -4. A little bit off there. So there's x equals -4. Lastly, there's going to be a point of discontinuity on this. And that is going to occur when x is 1. It's a factor of both the top and the bottom. And if you want to figure out exactly where that is, then you can cross these out. You'll have x plus 2 over x plus 4. And I just sub in 1. So 1 plus 2 is 3. 1 plus 4 is 5. So at 1 3/5. Okay, and that's going to be a hole. That's how I show that point of discontinuity. Now, using that information, I think it's pretty obvious what's going to happen on this part of the graph. And you might say, well, what's going to happen on the other? There are only 2 possibilities. Either it looks like this, or it looks like this. And the reason it couldn't be the red one is because then we'd have another x-intercept here. But we can see right here there's only one x-intercept. So in order for us not to have any more x-intercepts, it must be in that top left portion of the graph. Okay. So basically, it looks like one of those butterfly graphs, but it does have a hole right here, or a point of discontinuity. Okay, let's try another one. We want to get the same features out of this graph. If we want the y-intercept, well, that's going to be 0, 0, 0, 0. So 4 over -4. The y-intercept is -1 on this one. Might as well put it in. For the horizontal asymptote, let's take a look. Same power on top and bottom. So the horizontal asymptote is going to be degree of top divided by degree of bottom. Gives us y equals 2. And again, this is the same one that we did in example 6. Okay, to find the rest of what's going on, we need to factor. So common factor first up top. On the bottom, it's the same one that we had in the last one. So x plus 4, x minus 1. Let's keep going. This gives us a 2, x plus 2, x plus 1, all over x plus 4, x minus 1. Okay, now we're ready to do the rest of our analysis. X-intercepts. Those are going to be factors of the top only. So x-intercepts at -2 and -1. Let's put those in, -2 and -1. Vertical asymptotes. Those are factors of the bottom only. So they're happening at x equals -4 and x equals 1. Again, the asymptotes need an equals sign, an equation. So there we go. That's x equals 1. And here's x equals -4. We could have earlier put on this y equals 2 horizontal asymptote. Okay, and now we have to combine these. We look for points of discontinuity. There's nothing that's the same on top and bottom, so there are none. If I go through and try and connect my points, I think it's pretty obvious what needs to happen here. This will have to go through there and likely continue down. And then again, we have to think about what's going to go on. So on the far left portion of the graph, is it going to be up top or down low? Well, if it were down low, it would have another x-intercept. So it must be up top, like this. Same thing on the right-hand side. If it were down low, then it would have to pass the x-axis again. But there's no more x-intercepts. There's just these two that are over here. So it must look like this. Now, if you're really not sure, you can always put in a test point. So if you wanted to find out what's happening where x is equal to 2, well, that's no problem. You just put 2 into the original function, maybe into its factored form, because that would be a little easier. Okay, and we'd have 6 times 1. That would give us 24 over 6, or 4. The point 2, 4 is on the graph, so clearly it's up in this upper portion, if you couldn't reason it out. Okay, so that test point if you're in doubt. Same thing, you could do it at x equals -5. Okay, let's do one more where we're describing and then graphing. So over here, y-intercept, if I put in zeros for x, I'll have 2 over -4 or -1/2. Horizontal asymptote. Higher powers on the bottom, therefore y equals 0. X-intercepts, well, let's factor. This is going to be x plus 4, x minus 1. So same denominator in all of these questions. So you can expect to find an x-intercept at -2. You can expect to find vertical asymptotes at x equals -4 and x equals 1. And you can expect to find no points of discontinuity because there's nothing that's the same on top and bottom. Okay, before we do a whole bunch of thinking, let's just plot what we know here. So we know that y-intercept is at -1/2. 1, 2, x-intercept at -2. Vertical asymptotes at -4 and 1. Let's put this one in at 1 as well. Okay, and anything else? We know that horizontal asymptote is y equals 0. That's just the x-axis, so that really doesn't help us out that much. So these are the only points that we have to deal with. So we can probably assume that this does that, but I have no idea what is going to happen to the left of that. Maybe it's going to turn around, maybe it's going to go upwards as I move to the left. In terms of the far left, I have no idea whether it's this or this. And in terms of the far right, I have no idea whether it's this or this. So we really don't have enough information. When we're stuck, like I said before, the best thing we can do is get a test point and figure out what's happening. So I would really like to know what is going on at -3. Okay? And to do that, I'll just sub in -3 into either form of the original. I think that the factored form is going to be easier to deal with. Okay, so test points, -3. If I put -3 into this, let's see. That'll give me -1 on top, 1 by -4 on the bottom. That's going to give me a quarter. Hey, so now I know this point is right up here. So it follows that this must go upward. Okay, otherwise it would have to have another x-intercept. Let's find out for a test point what's happening when x is 2. So we'll know whether or not it's above or below the x-axis. So if I put in 2 to the original equation, that'll give me 4 over 6 by 1. 4 over 6, or 2/3. So there we go. I now know that I'm right here. And it follows from that that I must have this shape. Okay, now all that's left is the far left side. So a good test point would be anything that's to the left of -4. And probably the most convenient one would be -5. If I put -5 in the original, let's see, I'll have -3 all over -1 by -6. And that gives us -1/2. So there, I know that this point is on the graph. And since the x-axis is an asymptote, I know it must look like this. Now, the thing that might freak us out a little bit here is that we pass through the asymptote in the middle. The horizontal asymptote just talks about far right and far left. So we don't worry if in the middle it passes through our horizontal asymptote. It's just describing what happens to the far right and far left. And clearly this one is going towards 0 to the far left and far right. Okay, the last topic is rational equations. It's really a refresher because it was in your course last year. So to solve a rational equation, you need to find the lowest common denominator and also note the restrictions. Then you probably want to get rid of your fractions by multiplying by the lowest common denominator and solving. You'll double check to make sure your solutions aren't restricted values. So let's go through that process on this one over here. We'll start with the restriction. And the restriction is that the bottom, 3 minus 2x, is not allowed to be 0. Or x is not allowed to be 3 over 2. If you solve and you find that the answer is 3 over 2, you have to go back and say, no, that doesn't work in the original. Okay, we also might want to talk about the LCD. And the lowest common denominator in this case is going to be the only denominator you have, which is 3 minus 2x. From there, we multiply both sides by the lowest common denominator. And on the left-hand side, these are just going to happen to divide out. So we'll be left with x squared minus 3x minus 7. On the right-hand side, if I multiply those all out, I'll get negative 2x squared. I have a minus 3 at the end. And I'll have a positive 2x and a positive 3x. So positive 5x. Okay, rearrange. That gives us 3x squared. Because it's a quadratic, we want to make one side 0. And minus 4. You might try for a minute to factor that. It's not going to factor for us. So when a quadratic does not factor, our option is the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's throw them in. Negative negative 8 is 8. Negative 8 squared is 64. Minus 4 times 3 times negative 4 gives us a positive 48. And 2 times 3 is 6. We can go through and solve this exactly. So that's root 112. You can simplify this. Root 112 is 4 root 7. And you can take a trip down memory lane to simplifying radicals. Or you can just take my word for it for now. Okay, which simplifies to, those are all divisible by 2. So we'd have 4 plus or minus 2 root 7 over 3. Okay, the thing to notice here is that is clearly not the restricted value of 1.5, or 3 over 2. So these are both going to be okay solutions. If you wanted to do it and figure out what the approximate solutions are, well, you just go to your calculator and put in 4 plus 2 root 7, and then divide that by 3. Gives us 3.10 to 3 sig figs. And if we did the subtracting part, square root of 7, and then divided that by 3, we'd get negative 0.431. Okay. And you could have gotten those answers from this step as well. You could go straight here. So if you weren't sure about simplifying your radicals, there you go. You can still get the decimal approximations. They're not restricted values, so those are both fine answers. Or you could have given it exactly like this. Either one's good. We'll do one more where we're looking for the LCD. We're looking for the restricted values. And before you can find the LCD, you should always factor your denominators. Because if you don't, here's what you might think. You might think that the LCD is one of these times the other. And while it's true that that's a common denominator, it's not the lowest one, and it's going to make a big mess for you. If first we factor, we can see that they both have 2x plus 5 as part of the LCD. And we also need the 2. It also means that we only really have one restriction. The restriction that comes from 2x plus 5, that bottom, cannot be 0. Okay? Which means that 2x cannot be negative 5, or x cannot be negative 5 over 2. So that's all the groundwork. Now that we know that, and I'm just going to rewrite the whole question. Now we're going to multiply both sides by the lowest common denominator, which in this case happens to be the denominator of the right-hand side. Okay, on the right-hand side, things are going to be really easy. These divide out, we get 8x plus 15. On the left-hand side, the classic mistake is to divide out this 2x plus 5 here, which is fine, and get 2x. But it's only divided out for this one multiplication. Okay. When we go to multiply by 2x, well, we still have to consider that 2 and the 2x plus 5. Okay, so over here, those are going to divide out in this one. When we multiply into this, we'll have 2x times 2 times 2x plus 5. And that whole thing together is going to give us 8x squared plus 20x. Now we've got a quadratic. Let's move things around. So we'll have 8x squared. We'd have 22x minus the 8x gives us 14x. And minus 15. You can go to quadratic formula here. This one happens to be factorable, so we will. Okay, and that's going to give us solutions of x equals 3/4. And from this one, you'll have x equals negative 5/2. And we feel great. We circled them both. We say we solved this equation. But we need to look at the initial statement. Do we have a problem? Here was the restricted value. This is the only number that the solution's never allowed to be. And we found that one of our solutions was negative 5/2. That's no good. So we have to discount that solution. We go back and check against the restriction. That covers really most of Chapter 9. I'm going to keep going here with the slant asymptote if you're interested in figuring out how that all works. But this is the extent that you could expect to see on an assessment. Okay, so very last one for the diehards here. If we want to find out what this graph looks like, we've got x squared plus x minus 2 all over x minus 3. The y-intercept, again, we just have 0 zeros. So the y-intercept would be 2/3. Here's how we find the slant asymptote. We do long division. We take that x squared plus x minus 2, and we divide it by the x minus 3. Okay, so x squared divided by x is x. Multiply them back in, and I end up with this. Subtract gives us 4x minus 2. Okay, 4x divided by x is positive 4. Multiply it back in, we get 4x minus 12. Subtract it all off for a remainder of positive 10. And what that means is that you could rewrite that initial function as y equals x plus 4 plus 10 over x minus 3. They would mean the exact same thing. The slant asymptote is going to be the whole number and whole variable part of this, the x plus 4. And that's because if you think about this function as we go out towards infinity, far to the right, that 10 over x minus 3, that's going to become nothing. It's going to become insignificant with a big x value. The driver of the whole function is going to be that x plus 4 part. So we have a slant asymptote in this case of y equals x plus 4. Okay, I'm going to go and take this and factor it so we can do the rest of the analysis. And we can find out that we have x-intercepts at negative 2 and positive 1. We have a vertical asymptote at x equals 3. And we have no points of discontinuity. And this actually ends up giving us a neat shape. So x-intercept's at -2 and +1. Vertical asymptote at x equals 3. Y-intercept at 2/3 right here. And then there's this slant asymptote. It's got a y-intercept of 4, and it's got a slope of +1. So it's going to look like this. Okay, that is the line y equals x plus 4. Now if I go and make my curve going through these points and getting infinitely close to both the vertical and the slanted asymptote, that's what I get on that portion of the graph. And then in the other portion, I'll be sort of cradled between the asymptotes on the top right side. Okay, so that's a possibility if you end up with the highest power on the top. Again, don't expect that on the test. There is one that's like that on the review that's attached here. I hope that you found this helpful, and I'll see you later.